Okay, this third example in the mechanics one. This one's quite a long example, that's why I've created a separate video for it. I'm also doing it the other way round to what we did in the lesson, just to build up the whole situation. So now what we're going to do is we're going to actually have a situation with two boats, and they're going to be in a known position and moving in a known method. Okay, so we're setting up, and slightly change it, just because we can. So we've got a control tower for two aeroplanes. We're describing movements in kilometres per minute. So the first plane, A, is at a position -4,2. So its position vector is -4,2. Its velocity is 2,3. The second aeroplane is at a position vector of 4,4. I'll cut these in the final notes. Actually, let's do them now. Let's make a difference between the vectors for the motion and the vectors. So motion vectors are going to be in red. So draw red. I want the other one. Can move them. And the other one was doing -2, 2. And these could be kilometres per minute. This is distance in kilometres. The sort of things we're going to try and work out is what's happening, how does each plane move, how can we write a position vector for the plane generally, and then we'll go through solving a problem to find out, could these two planes crash? Are they on a collision course and that mechanics? That's where we had the long discussion during the lesson. So let's take the first part and let's try and write a position vector for an aeroplane. Now, in the start, we had general position for A is a bit like having a displacement is equal to a start displacement, i.e. a height above the land, plus the velocity times time. And this is assuming constant velocity, which these both have. The vector equivalent will be vector RA0 plus U vector A and times the time. Now this is actually an equation for a line in vectors form. The equation for a line in a vector is some point on the line, the one we want to find. This is any point on the line. And the next part is a pointer along the line, so the direction vector, and some scalar value we normally call lambda. We'll be doing more with equations of a line. This is exactly what this is. This is an equation of a line, and it's very similar to y equals mx plus c. Each part takes the same point. M gives you the pointer, lambda is the value you want to vary it along the line by, and c at some point we know on that line. And that's exactly what this is all to do with. Okay, so that's just a side note on the equation of line. Let's drop the things in for A then. So A, and I'm going to leave this in column form. I think I just said that. It's -4,2 plus its velocity vector, which is 2,3, and times it by time. And that will give me the position of A as a vector. So we get an x coordinate and a y coordinate. And we can take a little example of this, of saying, so in 1 minute, t equals 1, we would get RA is equal to -4,2 plus 2,3 times 1. So each of these are just 1, and we get -2,5. So after 1 minute, minus 2, up 5, 1, 2, 3, 4, 5. Oh look, it's on the end of that line, because we're saying one lot of this vector. If I say 2, so that's RA1, RA2. Start with the position on the line. Okay, so we're just putting the equation after 2 hours. We draw in the pen, so it's plus the 2, 3 times 2. So it's going to be 4, so we get to a position 0, 8. So the next place we've said it will be 0, 2, 4, 6, 8. And that's continuing this line. So it keeps going along that line. There's an equation for a line. We can also do the vector for the second plane. So R for plane B is going to be the X and Y for plane B. And we're going to use the same time. So we're starting, the position of B was at 4, 4. And the position, the velocity is going to be minus 2, 2. And velocity we need to multiply by time. So there's my equation of motion for plane B. And we can find out where it's going to be in 1 hour time. It should be here, so it should be 2, 2, 4, 6. So the position of R after 1 hour is going to be 4, 4 plus minus 2, 2 times 1, which gives me 4 plus minus 2 is 2, and 4 plus 2 is 6. So what we can see from the numbers is these planes are coming closer together, and now the question is, will they actually hit each other? Because we're using the same time, you can actually write, if they clash, then we have RA equals RB. If we try to do that, we'll get them at the same time. Trying to find a point where they both go through. They may cross, but it's whether or not they cross at the same time that's important. So it's at the important part is at the same time t, so you don't use a different variable t. We can put those in. So RA is minus 4, 2 plus 2, 3 t, and does that equal the B1 at 4, 4 plus minus 2, 2 times t. Rearrange them to bring the parts together, and we can do 2, 3 times t minus the vector part of the time on the other side, and this is equal to 4, 4 minus the vector on the other side. Factor out the t, and we can actually combine these two vectors together now. So we get t is equal to 2 minus 2, that's 4, and 3 minus 2 is 1. And does this equal, is there a value where we get 4 minus minus 4 is 8. And 4 minus 2 is 2. Yeah. Now, is there a value of t that will scale from 1 to 8 to both values? If these two, if you can't scale them both, then they will not collide. So when t equals 2, they collide. And it must be true for both I and j together. If you did them separately, what would happen here is you'd find out where they crossed in the I direction or the j direction. Okay, so it must be true for both values. So in this case, we would say the collide. A counter case would be something like where I get to no crash. Case would look something like 4, 1, and we have a position 8, 3. So when the time is 2 now, we would have them actually not being in the same place because the y paths would be different. That's one of the key parts. This is no crash because 4t equals 8 gives me one value, and t equals 3 is a different value. And they're actually telling you, depending on that, it's their I paths cross here. Are the same. And in this one, because we equated the j parts are the same. Because both of those are the same, we have a collision there in the same I and j at the same time. So that leads to this one crashing. There was another way to approach this second part, so I'll just copy the diagram forward. So this solution is more or less under the control of the control tower because the vectors are all based upon what's happening around the control tower, where the control tower is stationary. The alternative to this, which led to some discussion, is there is another way that this can happen if there's no control tower. So we've got no control tower, but we know where each other are. And we've got a question. So if I erase that as well. But we've got the same, we've now got a relative position. So at this time, if I can say this position, which was, so this position, we're going to say is 8, 2. So from A, these worked out, plane B is on that direction for him. Now he's going to try and work out, are we in collision? And the technique for this one is to try and turn it round to take everything as if A doesn't move. So we're going to try and fix A, because we want to see how does B move compared to plane A. Now, what we're actually trying to think about is if this origin is moving and they both move the same amount at the same time, what happens? What's the actual coordinates look like? So let's do that one there and make it that big. And do this one all the way over here, and I will do 2, 4, 6, 8 and 2 up, and I'll do that one slightly smaller. So we're going to draw underneath. What does it look like from A this plane is doing? So there's the plane and it's doing this 8, 2 thing. So B starts there and we're fixing A. Move time on 1 and we're now to here and here. And we've now got this 2, 4, 6 and 1.5. So from A we go 6 across and 1.5 up. So that's B at 0, B at 1. Move on again, another 1.5. Another 1 there. We've now got 1, 2, 3, 4 and up 1. So from here, from A, so counting what A is doing to get to B, we go across 4 and up 1. That's B after 2. So what we're actually doing is, by fixing A, we can see what B seems to be doing in the diagram. And that's what we mathematically need to do, is we're going to fix A and find out, is it on a track? What direction is it heading? And then we'll use the position vector to work out exactly whether or not it's going to collide. I think you probably realise they will do because it's the same situation. So to fix A, what we need to do is we need to take the velocity of A and set it so that it becomes 0. So we're going to make a correction value. We're going to say 0, 0 is the velocity of A, which is 2, 3. And we're going to add to that this constant to change this constant vector. And this fits the velocity frame, what's called the inertial frame. So we're going to say the inertial frame is going to be based upon a Cx and a Cy. By fixing A to make it 0, Cx and Cy, everything moving to this needs to be corrected by -2, -3. That's what we need to do to the velocity for B to make it fix. Effectively, what we're doing is turning this into a velocity vector of 0, 0, and this velocity is going to be a new velocity for B. So that was the velocity of A dash. No, let's not do dash because that's differentiation. Let's do A dot. So we're fixing A with VA. So fixing now B to make it inertial from B. Let's do VA. Let's do the velocity of B compared to A. Okay, fixed is equal to VB in the x direction, VBY. These are just the two values in the vector. So we start with our vector VB and we need to add the same correction. It's this correction vector that fixes A stationary. So it's -2, -3. VB is -2 plus 2. So the net velocity for VB is going to be -4, -1. So that now tells me which direction compared to A is the velocity going to be, which leads to -4, -1. So it's moving along this direction towards me at that speed. We can now do a position vector of B where A is fixed, which is its initial position, which was 8, 2. And add to that its velocity when A is fixed, -4, -1, and set that to T. And we're now going to solve the equation. If it collides, we get a RBA, that is 0, 0. That says it has come to the same location that A is. So 0, 0 is 8, 2 plus -4, -1 times whatever T is. Take the top line to make it true, T equals 2. Bottom line to make it true, T equals 2. So at the same time, I and J are the same. Here's a collision. So the pilot has now managed to work out that they're going to collide and something needs to happen.